Welcome and thank you for tuning in. My name is Danielle Gonzalez. I am a PhD student at Rochester Institute of Technology, and I'm very excited to talk to you today about a project that I worked on last summer as a Microsoft research intern, working with Tom Zimmerman, Patrice Godefroy, and Max Schaefer of GitHub. This project is called Anomalicious, the automated detection of anomalous and potentially malicious commits on GitHub. So malicious commits are a growing problem for GitHub and other open source software repositories because they can be used to conduct supply chain attacks where malware is injected into a package or dependency used by a lot of different systems. And then as those systems use them, it traverses down the supply chain. Here's an example of a supply chain attack on the event stream npm package. And what happened is there was a maintainer who was trusted by the repository owner who had given them push access to the repository. This maintainer pushed a commit that added an infected version of another package to the repository's dependencies. And then this was only discovered by another user who opened an issue. I highly encourage anyone who's interested in this to look at that issue. This person was able to backdoor inject malware into the repository through a commit. The question here, the motivating question, is how can we quickly and accurately detect malicious commits? And our solution was Anomalicious. The process is that a local copy of the repository is retrieved, a data pipeline mines the logs and uses the GitHub API to build a history of the repositories. And then though that data is fed into what we call a factor evaluator. The values of these factors are then given to a decision model who checks those values against a set of rules and uses a violation proportion to flag commits that it finds to be anomalicious. And the output of this process is a very descriptive anomalicious commit report that describes all of the rules that were broken and a bunch of other contextual information that allows a maintainer to make a quick and informed decision about any actions that may or may not need to be taken. We consider 5 factors in our decision model, and these are essentially properties for security related attributes that with certain values may or may not be suspicious. So we have file history, changes to sensitive files, pull requests, we look at outlier change properties, and then finally we have contributor trust, which is actually a decision model within our decision model. And so this is more of a socio-technical factor where we look at the author's interactions with the repository prior to this commit to make a decision about whether they are trusted or unknown. So this is the data pipeline that we use to sort of collect and organize all the data we need to compute the factors. And by organizing the data this way, it's very easy to calculate the factors that we've identified, and it's also highly customizable and configurable. You can include new factors or find different properties of these metadata fairly easily. Anomalicious uses a rule-based decision model. So the process works that all of the factor values are computed, and then a configuration file is referenced to see if the value meets a specific criteria. And if it does, then a red flag is raised, where a red flag is a rule violation. Then the flag proportion, so the ratio of raised flags to possible flags, is computed. And then we compare this proportion of violated rules or red flags to another criteria. And this is the master decision criteria. So this can be set to whatever you want, but by default, we usually use 50%. So if 50% of the factors had red flags, then we can call it anomalicious and a report would be generated. And so these are just example values, as I've mentioned. They can be configured to the specific needs of any repository. This is an example of an anomalicious commit report that would be generated for a commit that was flagged by our system. And it starts with contextual information at the top that helps the maintainer understand, okay, who authored this, who committed it, what message was there. And then the flag report starts with the proportion of rules that were violated, and then an enumeration with details of all of those violated rules. So you can see here that this person was trusted. If they weren't trusted, we would have also enumerated why. And they've changed 2 potentially sensitive files where we actually highlight what change was made and what proportion of commits to that file that this author had. And there's also outlier change properties. And again, we give extra contextual information about what that author's average values are for those outliers. We use 5 criteria for success to evaluate Anomalicious. The first is that it must be language agnostic so that it can be used by as many different repositories as possible without special language dependent configurations. It should be very highly customizable to suit the needs of different types and sizes and domains of projects. It must be able to identify malicious commits that we already know are there. And it must also have a low proportion of false positive commits flagged. And in this context, false positive means a commit that's totally benign and there's no reason why someone would need to take a further look at it. And then finally, we want to make sure that our reports are useful, that they provide enough context, the rationale is clear and easily to understand, and that maintainers can quickly and easily figure out what they need to do next. So we conducted our evaluation in 2 parts. The first part was looking at infected repositories to see how well the system could identify commits that we knew were malicious. And I will touch on this again later, but this is a very small data set. There are not many repositories who have decided to keep their malicious commits, so they were difficult to find, but we were able to find 15, 13 of which were infected with a malware known as octopus scanner malware, which infected Java projects that use NetBeans. Then we had our event stream backdoor injection, and then one other backdoor injection. So using this data set, we evaluated our tool using the following process. We ran the tool on all 15 repositories using the exact same set of configurations, and then we evaluated the commit reports that were generated for each individually. The results are very promising. The tool found the known malicious commit for 8 out of the 15 repositories. So this table here is showing how many commits were flagged and whether or not one of those commits was the malicious commit. A very small proportion of repository commits are flagged, even if they weren't malicious. So 60% of the repositories, less than 5% of the commits were flagged that weren't malicious, and for the other 40, there were no extra commits flagged. These results are very exciting and promising, but the disclaimer is that they are preliminary. We would need to redo these evaluations on larger data sets to understand a little bit more about how effective it is. But it is a great demonstration of the fact that it is possible to do this with this type of data, which has not been done before. Our other analysis was to look at sort of those commits that are being flagged that we don't know are malicious, and what are the properties of those commits. And so to do this, we took a data set of 100 npm package repositories. We did the same thing. We put them all through an Anomalicious tool using the same configuration file. And then we reviewed the reports for each repository. The results from this analysis were also very promising. 99% of the projects had less than 5% of their commits flagged. We also did a qualitative analysis looking at these commit reports to look for trends and patterns to figure out why they were being flagged. And we found that a lot of them were large refactorings that had to do with build tools. So we found that to still be interesting, even though they weren't malicious. There's a lot more information about that in the paper. I sadly can't go into it due to time constraints in this talk. So the implications of this work is that it's possible to identify malicious commits automatically without looking at the code, only looking at metadata and commit logs. We had very promising results for accuracy, and our false positive rate was consistently low. To emphasize that this is really a growing problem that needs to be addressed, these are attacks that have occurred between submission of our work and now. These QR codes link to more details to all of those incidents. But really, we need more data. As I mentioned at the time of our experiments, we only had 15 repositories with known malicious commits. So please, if anyone is aware of any other examples, to please tweet them to us at SaintsMSR, #Anomalicious. Thank you.
All right, thank you for the presentation. So I'm here with Danielle and Tom Zimmerman, who are ready to answer questions from the paper. I see a couple already in chat, so I'll start asking those. If you have other questions, please put them in chat and we'll ask them. So the first question from Amyangshu is, how did you come up with the rules and how many total rules did you have?
Sure. So the rules are based on the set of factors that we looked at, so sensitive files, things like that. And for each one of those factors, we thought about what characteristics or properties related to them would actually lead to some suspicion. So for example, there were 7 rules for the decision model, and the first one being a commit has touched more than a certain threshold of sensitive files. And so this can be configured to whatever the user wants. It could be one file, it could be all the files available. Or there's a lot of other rules based on the contributor's activity in the repository. So if the commit is not the author's first, but they're also not a majority contributor or owner of most of the files that they edited, so those types of things, they're very fine-grained conditions based on what was computed for the factors.
Okay, great. The next question then from Leandro is, how do you identify the files that hold sensitive data? Is the identification of these files manual?
Right, so for that, for the proof of concept that we built for this paper, we considered sensitive files to be those related to things like dependencies and build configuration. So we looked for a list of file extensions, so XML, JSON, jar, Gradle, things like that. They were not manually identified, but the system can also be configured to look for a specific set of files. So if you give it the whole file name and path, it could also look for that instead.
Okay, great. The next question from Rashmi is, do you have any insights on how generic your rules are? Do you imagine repository miners tweaking these rules?
The system was designed so that generic out of the box, it can be useful, but then it can also be fine-tuned by whoever's using it for their own purposes. So there's this sort of repository history that's built, and any of the data that comes from that you can use to create a rule. And so you can change the existing rules, you can change the thresholds, you can add new rules. It's highly customizable.
Okay, and the next question from Christina, which are the possible configurations, and is the approach available for use from practitioners?
So I'm not quite sure how to answer that as far as the possible configurations. As I've mentioned, you can use any values for thresholds and things like that. Anything that you can do, any data that you can get from these factors is really, it's up to the person who wants to configure it. As far as the approach being available for use from practitioners, we have not published a running instance of this tool yet. We're still sort of seeing how we can make things better based on new information that's come out since the time that we worked on this, and new techniques for building more intelligent models.
Okay, the next question from Jasmine is, from my understanding, Anomalicious could be seen as a security layer for GitHub repositories. When a report is admitted, what happens? Is the repository owner responsible for reviewing the report and taking action, considering that the commit would still be pushed? And again, that's assuming it's available for practitioners, which you said it's not now, but just kind of thinking about how it might work.
Right, so the sort of vision that we had before we began was that it would be like an alert that you would get for other activity in the repository, that the maintainer would see this report and be able to make a decision about whether any action is needed or not. So they wouldn't necessarily have to take an action. As far as considering the commit would still be pushed, ideally, this could be integrated in a way where it's sort of a scan pre-commit that could block that from happening, or for example, work somehow with pull requests. Yeah, so that way you could sort of intercept them as they come, but then you can also use it to sort of retroactively scan the repository and see if something might have happened that you weren't aware of in the past. such as if you find out about another exploit and you want to know if you've been affected.
Okay, great. The next question is from Fabio. He's got two questions. So if you were language sensitive, do you think you could have had better precision? So I'll ask that one, then I'll ask the next one. So if it was language sensitive, do you think you could have had better precision?
I'm not sure it would have helped with a lot of the factors that we considered, because the only one that actually really relates to the code itself is looking at file extensions. And a lot of the things that are used for build configuration may not necessarily be too language specific. We do consider things like looking for Gradle files and things like that, but the factors that we're using are a little more socio-technical, because we're trying to see, the point was to see if we could do this without looking at the code at all. So if we wanted to look at the code, that would probably have to be language dependent, and obviously we could get pretty far with that, but this is a more lightweight approach, and so it was an intention to keep it as language agnostic as possible.
Okay, then the second question is, one of your tested repositories had more than 70 false positives. All the others had only a handful. Do you have any explanation for why that might have happened?
Yeah, we did some exploratory case studies of the results, and we looked for patterns, like what combinations of rules were being violated and things like that. And the sensitive files were associated with a lot of these false positives. So it was a lot of people who were modifying these files who had not contributed to them very much in the past. So it seems weird if someone is adding or removing a bunch of dependencies from a file and they are sort of new to the repository. And so another part of that is that we tuned the model to run on all of the repositories with the same configuration. So if we had tweaked those settings for that repository, it would have probably had better results. And that's also that repository, the ratio of these to the total number of commits in the repository was still relatively low, very low percentage.
Okay, and we have a question from Xiaowei. Do the rules have any priorities in your settings? Is one more important than another? And do all the rules need to be met before there's a problem?
Right, so the rules don't have priority. The idea is that you sort of assess them all independently to see whether they were broken or not. And then you look at how many, so we have 7 rules, we look at how many were broken, and that gives you a flag proportion, right? So say you violated 50% of the rules. Then how many rule violations you want before you flag something. So if we set it to 50%, then that would be flagged. But if it was set to perhaps 75%, then that wouldn't be flagged. So you can sort of work that out, but there's not sort of a hierarchy for the individual rules.
Okay, and then Peter asked, do you have an ETA for the tool? He'd love to try it.
I don't. I just encourage people to stay tuned, I guess. Yeah.
Okay. Well, we have just about 45 seconds left or so. Is there anything you want to say, kind of where do you see this going? Like, what's the next steps in this work?
Sure. Well, as I mentioned, we did some studies to look at the different patterns and things that were causing both flags that caused commits to be flagged, even though they weren't malicious, and the ones that weren't. And we learned some things about ways to improve the tool. So for example, we're looking at a lot of negative things, like, pull requests not being merged, things like that, but we're not factoring in positive things to balance it out. So working on adjusting the factors, adding more socio-technical data, which is really the benefit of using this metadata approach, and then working on—
Sorry to cut you off. We have 5 seconds. So if you want to continue the discussion, go to the discussion